This is the propeller development platform that I've been working on as my latest project. It's got power to the breadboard and to some of the various components, but it still doesn't have a propeller chip in it. But I couldn't help resist playing with it a little bit, so I thought I would play around with the 555 timing chip. The following video is my understanding of how the chip works that I got from Make Electronics. My reading skills aren't the greatest, so if it's wrong anywhere, it's probably my fault and not the book's fault, so keep that in mind.
This is a diagram of the 555 chip taken from Make Electronics by Charles Pratt on page 158. This top part of the chip is a series of resistors that gives us references to the supply voltage. If we connected here, we only get 0/3 of the supply voltage. If we connected here, we'd get 1/3 of the supply voltage. If we connected here, we'd get 2/3 of the supply voltage. Or if we just connected straight to the supply voltage, of course we'd get the full voltage. The chip connects this line at the 1/3 and 2/3 spot, with the 1/3 voltage going to the logic gate A. So the logic gate compares pin 2 to 1/3 of the supply voltage. If pin 2 is less than or equal to 1/3 of the supply voltage, then it triggers the flip-flop. So when pin 2 goes low, it causes pin 3 to go high and pin 7 to go high. And it will stay in this state until logic gate B returns true. When logic gate B returns true, it flips the flip-flop back up, making pin 7 and pin 3 low again. So the flip-flop will go back up when pin 6 is 2/3 or greater than the supply voltage. And now we get complicated. The state of pin 6 is dependent upon the capacitor C4. Before we triggered this thing, pin 7 was going to ground. So the power coming through R4, the R4 resistor, was never getting to the C4 capacitor. But when we triggered this thing, then pin 7 went high, so the power had to find another way to ground, and that was through the capacitor C4. At a certain point, as the C4 capacitor is charging, pin 6 will become 2/3 or greater than the supply voltage, causing logic gate B to become true, which will cause the flip-flop to go back up, which will ground pin 7 and pin 3, which, when pin 7 is grounded, will deprive the capacitor C4 of power. And it will stay in that state until we receive a low on pin 2. So how long pin 3 stays high after it's triggered by a low on pin 2 is dependent upon how fast the C4 capacitor charges. And that depends on how large C4 is and how large the resistor R4 is.
Going on to astable mode, because it's a little bit more interesting in that it oscillates the 555, causing it to trigger itself on and off, on and off. So the best way to go about this is to start with pin 1 and satisfy its wiring requirements, and then go to pin 2 and so forth and so on. Pin 1 just goes to ground, so we just have to run a wire from it to ground. Pin 2 goes back to pin 6, so we run a wire from pin 2 to pin 6. Pin 3 is our output pin, and we're going to send it to the buzzer. pin 4 goes to power. Pin 8 goes to pin 7 through the 1K resistor. And it also goes to ground. It goes to power. Now pin 7 goes to pin 6 through the 10K resistor. So the last connection on pin 6 is a capacitor. And pin 5 gets a capacitor. Okay, and now all we have to do is ground the capacitors. And when we turn it on, we should get an annoying little buzzing noise. So as pin 3 oscillates between high and low, it's causing the elements in the piezo speaker to expand and contract, making the noise. And we can change the frequency of the sound it's making by changing either the capacitor or the resistor. Let's instead of having a 10K resistor, let's put in a adjustable resistor in the form of a photocell. Already getting higher pitch. Now when I cover up the photocell, it changes the pitch.